So as we move into section two, we recognize that a differential equation is typically a differential equation that relates our independent variable to various derivatives of our dependent variable. And these can come in so many different forms. So generically speaking, we can say that we have um, some function of our independent and dependent variables at varying levels of derivatives of our dependent variable. Now, we use the expression function loosely because our equation may not pass the vertical line test in that form of the word function. But we have various inputs, various variables and derivatives of our dependent variable. Another way of writing that is to write it in terms of our largest order. So the order of a differential equation is based on the largest degree of the derivative. So let's say we took a fifth derivative and that was our largest derivative, our highest order derivative. That would be the order of the differential equation. So sometimes we write it our order of our differential equation and equate that to the lower orders and our dependent and independent variables. So once we denote that, then we could say that phi of x, if we substitute that into one of the above, so if we have, let's say, a third order differential equation, so we have third derivatives, second derivatives, first derivatives in our function. If we substitute this and its subsequent derivatives into a differential equation, so if we substitute in for y into either one of those equations, and it satisfies the expression, or satisfies the equation, making it a true statement, then we say that that is an explicit solution. Now you might say, why explicit? That's to be contrasted with implicit. Remember back in Cal 1 when we took implicit derivatives, implicit derivatives were of functions that were not solved for a single variable. They had x's and y's mixed together. So explicit just means that you have all of your independent variables on one side, your dependent variable on the other side. So if we have some function of our independent variable such that when we substitute it and its subsequent derivatives into our differential equation and it satisfies it, then that's said to be an explicit solution. And we'll look at an example of that in a moment. Sometimes we're not able to come up with a function that is merely of our independent variable. Sometimes we have something that is a mixture of our independent and dependent variables. So if we have a relation of this format, such that when we substitute this in to our differential equations, that it satisfies our differential equation, then this is referred to as an implicit solution. Again, being that this one is solved for our independent variable, this one has our dependent variables mixed together. And the way we determine that this one is a solution is a little bit different, because since it's not solved explicitly for a single variable, if this is a solution, typically what we do is we take the derivative of this. If our differential equation that we're looking for its solution is a first degree differential equation, then we take a first derivative of this implicit or this potential implicit solution and we rewrite it and see if the derivative of this matches our differential equation. If this were to be, if our differential equation were to be a second order differential equation, then we would take this potential solution, we would take two derivatives of it, and then we would see, does that potentially match our original differential equation? So let's look at a couple examples. So let's take a look at these two examples. So here's one. We're given a differential equation, and we want to check to see that this is a solution to this differential equation. So you could call this phi of x, you could call it y. I'm just going to leave it as phi. So if this is phi, we need the second derivative. So if we take the first derivative, the derivative of x squared would be 2x. If we take the derivative of this, we're going to bring the negative 1 down, so we're going to have minus negative 1 x to the 1 less power. So that's 2x plus x to the negative 2. And now we need the second derivative. So the derivative of 2x is 2. If we bring the minus 2 down, we're going to have minus 2 x to the 1 less power. So we want to verify that when we substitute, when we replace the second derivative of y with the second derivative, and we replace y with this, that it is a solution. In place of the second derivative, we're going to put 2 minus 2x to the negative 3. We're replacing y, so our coefficient remains 2 over x squared, and we're replacing y with x squared minus x to the negative 1. And if that's a solution, that should equal 0. So we replaced our second derivative, we replaced y, and let's see what happens. So there's some simplifying we can do. We can distribute here. So we have a 2 minus 2x to the negative 3 out front. If we distribute here, we do this times that x squared and that x squared cancel, leaving us a minus 2. X to the negative 1, we could also call that 1 over x. So when we distribute here, we have a negative times a negative, that's positive. We have a 2 times 1 on top, and on bottom, x squared times x, so x cubed. And then we have 0 on the other side. So notice 2 minus 2 cancels. X to the negative 3. 3 on bottom. These are opposites, so those cancel. So we're left with 0 on the left, 0 on the right, which is a true statement. So when we replace y with that function, and the second derivative with the second derivative of that function, we come out to a true statement. Therefore, that is a solution to our differential equation. That's an explicit solution because it's solved explicitly in terms of our independent variable. Now let's look at this one. Here's our differential equation. They tell us an interval, and they want us to show that this implicit equation is an implicit solution. So show that this is an implicit solution of that differential equation on that interval. Now you might say, why are they giving us an interval? We might see that here momentarily. Might not, but we might. So this is an implicit equation because it's not solved for x or not solved for y. So let's take this equation and let's take an implicit derivative. So we're going to take a derivative with respect to x because our differential equation is dy dx. So the derivative is with respect to x. All right, so to take a derivative of y squared, we bring the 2 down, y to the 1 less power times the derivative of y with respect to x. Remember our chain rule. It's the derivative of this times the derivative of the inside. The derivative of y with respect to x is dy dx. The derivative of x cubed, bring the 3 down, x to the 1 less power. The derivative of a constant is 0. On the right side, the derivative of a constant is 0. Let's solve this for dy dx. So move the 3x squared over. Divide both sides by 2y. So dy over dx is 3x squared over 2y. And that's the differential equation that we ended up with. Or that we started with, I'm sorry. So this equation, when we take the derivative, it produces that differential equation. Therefore, that is an equation whose differential equation is this. So this is an implicit solution of the given differential equation. Let's check another one. Let's check this one and see if this is a solution to the bottom differential equation. And this would be implicit because it's not solved for x or y. So if we take the derivative with respect to x of that implicit equation, the derivative of x is 1. The derivative of y with respect to x is dy dx. The derivative of e to the xy, well, let's look at that. What is the derivative of e to the xy? Well, the derivative of e to the u is e to the u times the derivative of the exponent. So the derivative of e to the xy will be e to the xy times the derivative of xy. Well, what is the derivative of xy? Well, that's a product. So the product rule. That's the derivative of the first times the second plus the first times the derivative of the second. Well, the derivative of y with respect to x is dy dx. So when we do e to the u prime, this is e to the u prime is y plus x dy dx. So e to the power times the derivative of the power. And then the derivative of the right side is 0. Now the question is, does that look like what we have there? Not exactly. So let's get rid of the parentheses we have. Notice that in our differential equation that we started with, that we're checking to see whether our implicit equation is a solution of, it has dy dx on the outside of a parenthesis. Or we could say dy dx is a factor of those two terms. So let's get rid of the parentheses here and see if we can collect the dy dx's. So we have a 1, we have dy dx. When we distribute here, we can call that y e to the xy. When we distribute here, we can call that x e to the xy dy dx. And then here we have 0. So let's collect the dy dx terms. I'm going to put those out front, and I'm going to go ahead and factor out dy dx. So if I factor dy dx out of this term, I have an understood 1 as the coefficient. If I factor out dy dx out of this term, I'm left with e to the xy. and then we have a y, or I'm sorry, a 1, and we have a y e to the xy. We've already taken care of the dy over dx terms, and we have a 0 on the other side. And if we check, that's exactly our differential equation. So the equation that we began with, is that a solution to this differential equation? Yes. When we differentiate it, we get that differential equation. So this is an equation whose differentials produce that differential equation. So yes, that is a solution. The last thing that we'll look at in 1.2 is the existence and uniqueness of a solution. Existence and uniqueness. So one thing that's mentioned in this section are initial value problems. So what do I mean by initial value problems? Let's suppose I have a differential equation, and going all the way back to Cal 1, we've solved some basic differential equations like this. The derivative of some function is 3x squared, and then if we integrate both sides, if we move dx over and integrate, we get that y is x cubed plus 2x plus some constant. And if we don't have some value that our equation has to satisfy, then this gives us a whole family of solutions. But if we are given some initial value, for example, that when the x value is such, the y value is something else, if we're given that, then we can find the specific solution of our problem. So this is the entire setup. This is a differential equation with a given initial value. And one thing that we saw is that the degree of the differential equation also dictates how many initial values we need. This is a first order differential equation. When we integrate this, we get one arbitrary constant, so we need one initial value to be able to find c. But if this was a second derivative and we had to integrate twice to get our function, then we would end up with two arbitrary constants, so we would need two initial values. We would need one initial value at the function level, one initial value at the derivative level to find each of those constants. So as we're working through this, if we are given a problem, we don't want to work through a lot of complex integration or different things if the solution doesn't exist. If we have a problem and the solution is non-existent, then we don't want to look for something that doesn't exist. And sometimes we can be aware of that before we even get started. Also, we want to make sure that when we find a solution, that's the solution and not just one of many. So let's think about the example where, and I'm not going to draw it exactly to scale, but if we were to integrate and get a family of solutions, we might have something like this. So our curves would go like such. And then depending on what specific point we had to go through, that would dictate which solution we're referring to. So all of these curves might have a y equals x cubed component to them, but they would be different based on their vertical shift. So we would want to know which specific one applies to our initial value. So there's a unique one. This one does it, this one does it, this one does it, this one does it. So there is one unique curve that is the solution to our initial value problem, which consists of the differential equation and the initial value. Now again, this initial value and this differential equation don't necessarily pertain to this drawing, just using this as an example. So what do we need to know whether our solution or whether a solution exists and whether it's unique? So the book says, let's look at the initial value problem. dy over dx equals some function of x and y. And this is our initial value. So this is our differential equation. Here's our differential equation. Here's our initial value. So this is the IVP. So if that function and if the partial, it's not a good partial, if the partial of that function with respect to y are continuous, and not just continuous anywhere, but continuous on some rectangle R, such that points x, y, x is between some a and b, y is between some c and d. So basically that gives us a rectangle, points from a to b, c to d. And that rectangle contains the point somewhere in there, x naught, y naught. One thing that's important to note is that x naught, y naught is an interior point. It's not on the boundary of the x and y intervals that are described. So when we draw that rectangle, our initial values are interior to that. So if these are true, and we can find some region, some rectangle, such that our initial value is on the interior point, then our initial value problem has a unique solution. If that's not true, then we don't have a unique solution. But if that's true, we do have a unique solution. So let's look at two examples of this. So let's try to see whether the existence and uniqueness guarantees a solution to this particular differential equation for dy equals, let's call that 3x plus 4y. So we're going to call f 3x plus 4y. And then the partial of f with respect to y, we take the partial with respect to y, we get 0 here, the derivative of that is 4. So what did our theorem say? It said that these have to be continuous on some rectangle with which this is an interior point. So let's check this one. So if we take f and put a 0 for x and a 3 for y, we would get 3 times 0 plus 4 times 3, which is 12. So we are continuous at that point. The question is, are we continuous at a rectangle that includes that point? So if this is 0, 3, if we go to the left of 0 or to the right of 0, are we still continuous? So if we put a 0 in for x, we get an answer. If I move a little bit to the left of 0, 3 times numbers on either side of 0 still give us an answer. So if I go this way or this way, I'm still okay. How about in the y direction? If I go above 3 or if I go below 3, I'm still okay. Because substituting 3 in for y is good. If we substitute something a little bit less than 3, we're okay. Something a little bit more than 3, we're okay. So we can go in either direction. So there does exist a rectangle that includes our initial value for which that function is continuous. Now we also have to check the partial with respect to y. What is the partial with respect to y when x is 0 and y is 3? Well, notice our partial is a constant. So regardless of x and y, we always get 4, which means that no matter what our input is, we always get an answer. So for our partial, this is also going to be true. If we're at 0, 3, if x goes a little bit smaller or a little bit bigger, that's still going to be continuous. If y is a little bigger or a little bit smaller, we still get 4. So that point lies inside a rectangle such that every point inside that rectangle is continuous on the partial with respect to y, and we already said it's continuous on the function f, which is what our derivative equals on the from points around 0 to 3. So we just have to verify that 0, 3 is an interior point that we can go in any direction. Might not be infinitely in any direction. In this case, we could go as far as we want in any direction, but at least a little bit in any direction and still have a point that makes our function and the partial continuous. And remember, our function is what our dy dx is equal to. Now let's look at this one. Our dy dx is already isolated, so f is what's on the right. And if we wanted to take the partial of that, let's change our notation and call that y minus 2 to the 1/2. So the partial of f with respect to y, the derivative of the first term with respect to y is 0. For the next term, bring the 1/2 down, y minus 2 to the 1 less power, times the derivative of the inside. So we get negative 1 over 2 square roots of y minus 2. So that's our partial with respect to y. So we have to see if 1, 2 is an interior point for some rectangle such that this function is continuous and that function is continuous. If we can find any point that's connected to this one that would be essentially touching this, for which either one of these are undefined, then we're not guaranteed to have a unique solution that exists. So first of all, let's look at f of 1, 2. If we put a 1 in for x and put a 2 in for y, we get 1 squared minus the square root of 0. So 1 minus 0, and we get 1. So that's okay. But when we have square roots, remember, we have to be careful, because if we end up with a negative number under the radical, we can't do that. That becomes imaginary, and we're only looking for real solutions. We're not looking for imaginary. So when y is 2, we end up with a 0 underneath the radical. If we pick a y value that's any smaller, infinitely smaller, or just infinitesimally smaller, 1.999999999, if we put that in for y and subtract 2, we're going to get a negative underneath here. So that means that all y values, in order for this to be continuous, have to be bigger than 2. If you think about finding the range of this, that expression underneath the radical has to be greater than or equal to 0. So all y values have to be bigger than or equal to 2. Well, 2 is where our point is. So that means our rectangle can't go below that. It can only go above that. Now, in the x direction, it's okay to have x's that are smaller than 1 or bigger than 1, because we can square anything. So if 1, 2 is our initial value point, we can go left and we can go right and we can go up, but we can't go below it. So 1, 2 is not an interior point. If that's not true, then we're not guaranteed a unique solution that exists here. So that's how that theorem fails. That's the case where we may not have a solution.